I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. And today is lecture number 14, and this is the last lecture, and where we are not going to see any new concept or idea. We are here to mini assessment discussion, and this lecture we will have just a revision of whatever we seen in this course, and we will have some practical example and some questions related to the whatever we just learned in this course. So I am Amraraj Sawant, assistant professor from Department of Mechanical Engineering. So final recap. So here we are going to cover a scope of heat transfer. So where the heat transfer going to apply in real world and engineering applications. What are the types or what are the modes of heat transfer, that is conduction, convection and radiation. So what are the practical applications and mini assessment discussions, means some questions are there, multiple choice questions are there, and while attempting that question you are going to visualize the things, and in everyday life if you are countered with any application or any example, so you are going to think that what type of heat transfer is going to take place in that scenario. So thermodynamics versus heat transfer, we have seen that what is the difference or main difference between the thermodynamics and heat transfer. While the thermodynamics is encountered with an equilibrium things, and in heat transfer we are not dealing with equilibrium things. That means in heat transfer, if the system or both two objects having same temperature, then heat transfer will not take place. There must be some temperature difference. This object must be at a higher temperature and this object must be at a lower temperature, or I can say that there must be a temperature difference to transfer the heat from one side to another side. But in thermodynamics, the equilibrium state we are analyzing it. So thermodynamics is nothing but energy and equilibrium, and heat transfer is nothing but the rate and the mechanism of energy movement, how the energy is moves from one place to another. There where the heat transfer analysis takes place. So right now we are going to recap the modes of heat transfer. First, in a conduction, the Fourier law is a governing law, and its equation is Q is equal to minus K dt by dx, and for 1D means one dimensional steady state conduction equation, we have derived one equation dou square T divided by dx square is equal to 0, and this equation we are going to apply for a single wall, and for that wall the temperature profile or intermediate temperature Tx we are going to find out, and its formula is Tx minus T1 upon T2 minus T1 is equal to x divided by L, where Tx is a temperature, we have to find it at a x distance. Okay, L is a total thickness or total length of that metal piece. T1 is a one side temperature and T2 is another side temperature. So thermal resistance in multi-layer system, as we have seen in a conduction, the composite wall in series and parallel, how the thermal resistance is going to change in series system. As you have learned in a 12th standard, the electrical analogy for resistance, same analogy we are going to apply here for thermal resistance. So in series the thermal resistance is just going to be add for total. That means the total resistance is equal to R1 plus R2 up to Rn, and in parallel the total resistance is a reciprocal, means 1 upon R total is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 up to 1 upon Rn. So that is how we are going to calculate the thermal resistance in multi-layer system, that is means series system or parallel system. So convection recap. In convection we have encountered with two types. First is a natural convection and second is a forced convection. And in natural convection happens due to density difference, and that density difference is created due to the temperature difference, and this density difference is creating convection current, and due to which the heat transfer takes place. But in forced convection we use external devices like pump, blower and fan to transfer the heat from any solid to that fluid. The fluid motion is controlled by the external device like pumps, fans and blowers. So in convection the governing equation is obtained from Newton's law of cooling, where its mathematical form is Q is equal to H AS multiplied by TS minus T infinity, where Q is a total heat transfer to be achieved, H is a convective heat transfer coefficient, AS is a surface area that is encountered with a heat transfer, Ts is a temperature of that surface, and T infinity is a ambient or surrounding temperature. So convective heat transfer coefficient plays an important role in a convection, and it is not just a material property, it is vary with the flow of or flow properties or that fluid properties. So radiation recap. In the radiation we have seen that emissivity and black body. What is the emissivity? That is epsilon, which is emissive power of any object to the emissive power of a black body. Emissive power of any object to the emissive power of black body. And what is a black body? The black body is the any kind of object which is imaginary. It is not in the real form, so it is imaginary object that is completely absorb any radiation, or they that object is completely emit energy from its own, so will absorb all radiation and will also emit all radiation. So it is not possible in real sense. That's why we have taken gray body as our real case for radiation heat analysis. So for radiation, the Stefan-Boltzmann law is a governing equation, where the Q is equal to sigma T raised to 4, and where we have seen that as the temperature increases, the heat transfer will extremely or randomly increases because of this fourth power or nature of this temperature and fourth power, and where the sigma is a Stefan-Boltzmann constant equal to 5.67 into 10 raised to minus 8. So surface to surface radiation, here we have seen that the view factor and its uses in real life or general life and in an engineering application like a spacecraft. So how much energy is going to transfer from one surface area to the another surface area in fractions. So that is one of the most critical and somewhat complex mathematical form. So that's why we here for just introduction we are not encountered with that mathematical form and derivation, but in your core subject as a heat transfer, so you are going to see that mathematical form in the subject. So what are the applications? So in general life, cooking utensils, refrigerator, car engines and industry machines, you have seen the what types of heat transfer. Actually there are all types, that is what I mean to say, the all modes of heat transfer are acted simultaneously in all situations. More or minor means more or less or higher side, but all modes are present in actual practices. So here you can see the image, building insulation is there, and here you can see the image for engine cooling system. The coolant is poured and the utensil, cooking utensil, where the heat transfer takes place. So what is the purpose of this mini assessment? while we have conducted 13 lectures before, and in that lectures we have encountered with all the concepts, how the derivations or what is the purpose and what is the major relevance in a real life application and the engineering application. So just to brush up or just to revise the things, so that so that throughout your engineering you don't face any difficulty regarding the basic concepts in this heat transfer. So reinforcing the concept is a main purpose, clarify the problem solving or clarify the how to implement any concept to the real life example, and identifying common pitfalls. I mean, just like I have said that I have repeated these terms so many times: conduction, convection, and radiation, and what are the different types or how they are differ with each other. So while you are encountered with some application in your day-to-day life, then you can realize or recognize that okay, so this is the conduction state or this is the convection state, and if the radiation is more or if the flow of air over the hot plate is lesser, then there will be the radiation more. So these concept clarification or this concept building is a necessity. That's why I have kept this lecture for just to revise the things. So daily life application, just before in this image you have seen this home insulation. So in home insulation, the insulated wall roofs reduces conduction, it improves energy efficiency and lowers heating and cooling cost or cooling loads. That's why if you put more insulation over your walls in the buildings, we can have inner temperature more or constant. So to extract the heat by using air conditioning system, that should be minimized. So engine cooling, you have seen the cars over many times. So the coolant absorbs the engine heat by the conduction way, and in engine cooling the radiator transfer it heat to air by the conduction mode, and this prevent overheating. And why it is so? As simple as that, before I have given an example of a spacecraft. There also, if the overheating takes place, then the component failure chances may be there, and the total system may be failure, so maybe fail. So that's why, to prevent overheating, the cooling system is provided in engine, and in a spacecraft there is a insulation provided to minimize the heat transfer from outside to the inner components. So cooking utensils is a daily daily life your example of why it is made of copper or aluminum for high thermal conductivity material, so that your whatever the food you are going to cook will cook easily and fast. So to ensure the uniform heat distribution, that's why these metals are preferred of high thermal conductivity, so that the heat can transfer easily. So basically the idea behind this mini assessment discussion is that there is no condition in real life. Likewise, we have to minimize heat transfer. There are certain conditions where we require higher or more heat transfer, like in a cooking utensil. So depending upon the application, you have to apply this idea in general life or in your engineering applications. So right now we are going to see the conceptual question. Before just I have explained these slides. So based on that on these slides, I have just kept two questions, just simple questions. Condition is that a metal rod is partially inserted into the furnace, and one end is glowing red inside the furnace. So let's say this end is glowing red, means it becomes red inside the furnace, and while other end is outside the room temperature. So other end, so this end just we kept at a room temperature. So question is that which mode or modes of heat transfer are possible for the temperature increase along the length of the metal rod. The question is what? How the heat transfer will take place along this length of metal rod from higher temperature to the room temperature. So just I have given this example in a conduction heat transfer mode. So right answer is a conduction only. But actually in actual practices the convection also present in still air, the natural convection also present, but to be specified, to for temperature increase along this length or decrease along this length is only because of conduction. You understand it? If you don't, then please ask me in the discussion forum. So conceptual question number 2, let's say this pot is there, a pot is placed on stove and the flames are heated the base of the pot, and inside the pot the water bubble rises in a and circulate. Means what? The pot is kept on the stove and the stove is ignited, and here the water is placed inside that pot and the water bubble rises from bottom to top and they are in a circular form, okay, or water bubbles are just rising up. So question is that which primary mode of heat transfer is responsible for circulating the water inside the pot? So what is the mode of heat transfer is the main or prominent for getting that water bubbles from top to bottom? So this is the fluid, water is the fluid, and the heat is going to transfer from this hot pot, okay, or stove to hot pot, and again that hot pot from this fluid which is water, and when there is a fluid flow or there is a fluid over a solid metal or solid state, so then only convection happens is a basic idea. Have you got it? Okay, so final thought about this lecture or our course as a introduction to heat transfer, a practical oriented approach. So why this course is designed? Because while you are going to study this subject as a core subject in a third year, and there various mathematical forms are there, but just to juggle with a mathematical form is not our engineering thing. You have to understand the basic and concept behind the heat transfer or any subject, and whenever you understand the basic thing, then applying or then just converting it to a mathematical form is an easier thing. And when you just cleared your basic thing, then you can't forget these things throughout your life. Not only in this engineering 4 years, throughout your life, if you clear these ideas and basic things, then throughout your life you are not going to forget this. Okay, so the course summary, we have done these theoretical things and practical applications in this course. So some laws regarding the heat transfer and the modes of heat transfer, we have seen these. Some numericals and examples we have taken in this course, and real world application emphasis is a more stretched out thing in this course. Why? Because you have to understand how the heat transfer is going to apply in a real world. So I think so this will be helpful to clear your basic things regarding the heat transfer subject. So what is the next step to do? So I will give you one design based project. In that you have to analyze or you have to think what type of heat transfer mode are going to apply, and we have seen the governing laws or governing equation, which are simply we have to just apply that things to the one project, design based project. And we are also going to see industrial case study, which is actual study, which is actual problem from industry, and for that problem also same thing we are going to do, what type of modes of heat transfer are applicable to that specific case, and how the heat transfer is going to be, and how much is heat transfer is going to be, and the calculations behind that you have to do that. So you can access online links provided for discussion forum in this course in a discussion forum box, and the lecture notes and ebooks of this course will be provided in same discussion forum. So you can access every lectures PDF notes and the ebook for this total entire course. As an ebook, I am going to publish this ebook as a introduction to heat transfer, a practical oriented approach. So you can find these things in the discussion forum box. So thank you very much for this course, and feel free to ask me anything about this course or any conceptual doubts of yours in the discussion forum. Thank you very much.